We have officially entered the era of necrobotics, where engineers are literally reanimating the corpses of dead spiders to perform high-precision mechanical tasks that our best synthetic robots still can't replicate. You have probably seen a dead spider in the corner of your garage or under a bookshelf, and you likely noticed how its legs were all curled inward toward its center like a tiny, skeletal fist. For a long time, most of us just assumed that was some version of rigor mortis, or just what happens when something small and spindly dies. But the reality is actually much more fascinating, and if we are being honest, a little bit haunting. Spiders don't actually move the way we do because they don't have antagonistic muscle pairs to extend their limbs. So when they die, they don't just go limp, they lose the ability to maintain internal pressure. This realization is what led a team of researchers at Rice University to look at a dead wolf spider and see something other than a piece of biological waste. They saw a perfectly engineered, ready-to-use mechanical gripper that had been refined by millions of years of evolution. This is the birth of necrobotics, which is exactly as intense as it sounds, because we are talking about using biotic materials as robotic components. It sounds like something pulled straight out of a gothic sci-fi novel, but the implications for the future of engineering are massive. The problem we've always had with traditional robotics, especially at the micro scale, is that manufacturing tiny, delicate, yet strong moving parts is incredibly difficult and expensive. We try to build these intricate systems out of plastic and metal and silicon, but we are constantly fighting against the laws of friction and the limitations of our own manufacturing precision. But then you look at a spider, and you realize that nature has already solved this problem with a design that is both lightweight and surprisingly powerful. To understand how they actually hijack these creatures, you first have to understand the spider's internal plumbing. Most animals use muscles to pull limbs in both directions, like how your bicep curls your arm and your tricep extends it. Spiders, however, only have the muscles to pull their legs inward. To push them back out, they rely on a hydraulic system. They have a chamber called the cephalothorax that acts like a central pump, and when they want to move, they send a surge of hemolymph, which is essentially spider blood, out to their extremities. This pressure forces the legs to straighten out, and when the pressure drops, the legs naturally curl back in. It is basically the same mechanism you see in those long paper party blowers that uncurl when you blow air into them and snap back when you stop. But because this system is purely mechanical and relies on pressure, it means that even after the spider is dead, the hardware is still functional. The researchers realized that if they could just find a way to tap into that central pump, they could take over the controls. They took a dead wolf spider and inserted a needle into the cephalothorax, then sealed the connection with a tiny drop of superglue. By doing this, they created a hermetic seal that allowed them to inject small puffs of air into the spider's body. The result was both incredible and deeply unsettling because the spider's legs began to move again. With every puff of air, the legs would spring open, and when they released the pressure, the legs would clench shut with enough force to actually grip objects. But this wasn't just a parlor trick or some macabre science experiment meant to shock people. Therefore, the team began testing the actual performance metrics of these necrobots to see if they could hold their own against synthetic alternatives. What they found was that these biological grippers were capable of lifting more than 130% of their own body weight. They were able to pick up delicate items like circuit board components and even other spiders without damaging them, which is a level of dexterity that is notoriously hard to program into a traditional metal claw. But then things got even more interesting when they tested the durability of the spider's joints. You might think that a dead biological structure would fall apart immediately under the stress of repetitive movement, but these spider grippers were able to go through 1,000 open and close cycles before the joints began to show significant signs of wear and tear. This is where the curiosity loop really starts to tighten, because if we can use a dead organism to outperform a machine, it forces us to rethink what a robot even is. We usually think of robots as things we build from scratch, but Necrobotics suggests that we can treat nature as a source of prefabricated parts. It is essentially the ultimate form of upcycling. But there is a catch because as the spider's body dries out over time, the tissues become brittle and the hydraulic system starts to fail. This led the researchers to experiment with coating the spiders in thin layers of wax to keep the moisture in, which significantly extended the lifespan of the gripper. So we are looking at a future where we might see these biological components used in assembly lines for microelectronics or in environmental sensors that are meant to biodegrade once their job is done. That is one of the biggest advantages here. If you lose a traditional robot in the forest or the ocean, you've just added more plastic and heavy metal to the environment, but a necrobot is just organic matter. It will eventually break down and return to the Earth without leaving a trace. However, this also brings us to a very strange ethical and psychological crossroads. Even though these are just spiders, there is an inherent ick factor to the idea of reanimating dead tissue for labor. It feels different than using wood or leather because the movement is so lifelike. It taps into that uncanny valley where we see something that looks alive, but we know it is dead, and it is being puppeteered by a lab technician with a syringe of air. But from a purely pragmatic engineering perspective, the efficiency is undeniable. Why spend millions of dollars and thousands of hours trying to design a microgripper that mimics a spider when you can just use the spider itself? It is a shift from biomimicry, where we copy nature, to bio-utilization, where we simply integrate nature into our tech stack. This leads to a bigger question about what else we can repurpose in this way. If we can do this with the hydraulic systems of arachnids, what other biological mechanisms are sitting right under our noses, just waiting for us to figure out how to plug a needle into them? We are talking about millions of years of research and development that nature has already done for us, and we are only just now realizing that we don't have to start from zero every time we want to build a new tool. But you have to wonder if this is the start of a slippery slope. Today it is a wolf spider lifting a wire, but as we get better at preserving these tissues and integrating them with electronic sensors, the line between machine and organism is going to get incredibly blurry. We might see hybrid systems where the structural and mechanical work is done by organic, zombie parts, while the processing and logic are handled by silicon chips. It is a fusion that feels both inevitable and slightly terrifying. Imagine a world where your technology isn't just manufactured, but harvested, where the hardware of your devices actually has a genus and a species name. This isn't just about spiders, it's about a fundamental shift in how we view the material world. We are moving away from the idea that dead things are useless and toward a perspective where everything in the biological world is a potential component for a larger machine. But there is still so much we don't know about the long-term stability of these systems. Therefore, the next stage of research isn't just about making the legs move. It's about understanding the chemistry of the joints at a level that would allow us to keep them supple and functional for years instead of days. The researchers at Rice noticed that the failure point was almost always the dehydration of the internal membranes, which is a problem we see in traditional soft robotics too. But in soft robotics, we struggle to find materials that are both flexible and strong enough to handle high pressure. Nature already found that balance in the form of chitin and protein-based connective tissues. So the irony is that the more we try to build the perfect robot, the more we realize that the perfect robot might have already been crawling around in our basements for the last 300 million years. We are essentially just the latecomers trying to figure out how to use the tools that were already left on the workbench. It's a humbling thought, but it's also one that opens up a massive door for innovation. If we can get past our initial revulsion at the idea of zombie spiders, we might find that the key to the next generation of sustainable, high-precision technology isn't found in a clean room or a high-tech factory, but in the natural life cycles of the world around us. We are looking at a complete collapse of the boundary between biology and engineering, but then you have to consider the scale. If this works for a spider, would it work for a crab? Crabs also use hydraulic systems for certain movements, and they are much larger and stronger. Could we see necrobotics applied to heavy lifting or underwater exploration where traditional electronics often fail? The possibilities are endless, but they all lead back to that same unsettling image of a needle and a puff of air. It's a reminder that we are living in a time where the things we used to think were impossible, or at least deeply weird, are becoming the standard operating procedures for the people designing our future. So the next time you see a spider curled up on a windowsill, don't just see a dead bug. See a sophisticated piece of hydraulic machinery that is just waiting for someone to plug it in and give it a second life. It's a strange, brave new world where the dead are being put back to work, and we are only just beginning to see what they are capable of doing for us. But even as we celebrate these breakthroughs, there is a lingering sense that we are playing with a power we don't fully respect yet. We are essentially hacking the exit code of life to keep the hardware running long after the software has crashed. It's efficient, it's clever, and it's deeply practical, but it also forces us to confront the fact that we are increasingly viewing the living world as just another set of resources to be managed and manipulated. Whether that is a triumph of human ingenuity or a sign that we've lost our way is something we're going to have to figure out very soon, because the technology isn't waiting for us to be comfortable with it. The necrobots are already here, and they are stronger than we thought they would be. But as we push deeper into this field, the real challenge won't be the engineering itself, but the way we choose to use these reanimated tools in a world that is still trying to define where life ends and the machine begins. It makes you realize that the most advanced technology on the planet isn't something we built. It's something we are finally learning how to hijack, and that might be the most chaos twist of all in the story of human progress. We spent centuries trying to escape nature, only to realize that the best way forward is to reach back and pull it along with us, even after it's gone.